Good morning, all of you. Welcome to Sri Jayendra Zone. So we have completed lecture 1 in thermodynamics. Now we are continuing lecture 2 in thermodynamics. So it is based on work done and heat conversions in thermodynamics. So in the first lecture we have done already various types of systems in thermodynamics. Now next in this lecture we are going to do new topic. So that is thermodynamics and thermochemistry. IUPAC conventions for heat and work, very important, because in numericals you will get a lot of problems in this based on this concept. So that's why this concept is very important. Please follow it carefully. Let us see now what are the important IUPAC conventions. If heat is given to the system, Q is nothing but it is taken as positive. If heat is given to the system, it is taken as Q is taken as positive. If heat is taken out of the system, Q is negative. If heat is taken out of the system, Q is negative. If work is done on the system, here in physics it is different, but in chemistry we are doing this. If work is done on the system, W is positive, work done is positive. If work is done by the system, W is negative, that is work done is negative. For example, if 10 kilojoules of work is done by the system, then surroundings, then work done is equal to minus 10, because work done by the system is taken as negative. I hope it is clear. So work done on the system is positive and work done by the system is negative. Because why it is taken as negative? Because since work is done by the system, means system is losing its energy to the surroundings. So that's why work is done by the system on the surroundings is negative. And work is done on the system, since system is gaining the energy, so work done is taken as positive. In this case, what happens? System is gaining energy. System is gaining energy. That's why it is taken as positive. And in this system is losing the energy. System is losing the energy to the surroundings. Losing the energy to the surroundings. Hence, work done is negative. I hope it is clear. And heat is taken out of the system, Q is negative, and heat is given to the system, Q is positive. So these are the IUPAC sign conventions for heat and work. Very important. So in physics, it is different and chemistry, it is different. So that's why you have to understand, if work is done on the system, W is positive. If work is done by the system, W is negative. What is W? Work done. I hope it is clear. Next, internal energy. What is internal energy? So as I told you, internal energy is a state function. It is not a path function. It is state variable, and it is also it is also an extensive property. Internal energy is an extensive property and also state function. So I'm writing here again. It is an extensive property because its value depends upon the work. So extensive property because it keeps on changing, and also it is state function. State function. It is not path function. It is state function. So this is called internal energy. Now, what is internal energy? A given amount of substance system under the given conditions is associated with a definite amount of energy. So if a system is associated with a definite amount of energy, which is called the internal energy, it is nothing but all forms of energy, that is kinetic, potential, associated with the atoms and molecules in the system, are part of internal energy. So what is internal energy? The energy associated by the system is called its internal energy. It is an extensive property and it is also a state function because it's where its value will be changing. Its value will be changing. It is depending on the quantity of matter. It is depending on the quantity of matter. That's why it is extensive property. I hope it is clear. Next, let us see what is internal energy continuation. It is a sum of translational, rotational, vibrational, electronic energy, and any other form of kinetic and potential energy. So this is called total internal energy. So internal energy is equal to the translation energy of the system, rotation energy of sum of the translation energy, rotation energy, vibration energy, electronic energy, and others of the system. That is like kinetic energy and potential energy of the system. So this is called internal energy. It is the sum of all the energies connected with the system. What are the energies connected with the system? translation energy, rotational energy, vibrational energy, electronic energy that is based on the electrons, and kinetic energies and potential energies. So the total sum of all the energies of a system is called its internal energy. And this will be changing by giving some energy or by taking out some energy. So if the system is losing energy, its internal energy changes. If the system is gaining energy, its internal energy also changes. So that's why it is depending on quantity of matter. It is depending on what? Quantity of matter. So for example, if your work is done on the system, then what happens? Its kinetic energy of the system increases. As the kinetic energy of the system increases and potential energy also increases, or translation, rotation, any of these will increase, the internal energy will change. The internal energy of the system will change. So that's why internal energy is a extensive property. It depends upon the quantity of matter, and it is nothing but the total sum of the translational, rotational, vibrational, electronic, and any other form of kinetic and potential energy. It is called as internal energy. I hope it is clear. Next. The absolute value of internal energy of a system cannot be determined, but the difference in the internal energy during a process can be determined. That is, change in internal energy is equal to final internal energy minus initial internal energy. Suppose, for example, if a system does work, so by giving energy or by gaining energy or by losing energy, we can say it reaches to a final state. That is nothing but the internal energy of the system will change, and that change in internal energy of system is called final internal energy. This U2 is called final internal energy, U1 is called initial internal energy. And we cannot exactly determine the internal energy of system, but we can easily determine the difference in the internal energy during a process. So for example, suppose a man walks on a road. So what happens? The internal energy of the person, the internal energy of the system. Here I'm dealing the internal energy automatic, the internal energy of system of the person, of the man changes. Either he gains energy or he loses energy. In this case, he loses energy because he is walking. So he burns some calories. He burns some calories from his body. So that is nothing but he loses it since his internal energy is decrease. So he burns some calories. So again, after eating some food, again his internal energy will be increased. So that is called the internal energy of the man changes when he burns some calories. So that is nothing but what? Internal energy. The same will apply for system also. So when a system is gained energy or lose energy, automatically its internal energy will change. And we cannot find the absolute value of internal energy of system. We cannot find the absolute value of the internal energy of system, but we can find we can find the difference in the internal energy during a process, and that can be defined by using the formula delta U is equal, that is called change in internal energy, is equal to U2, that is internal energy of the final minus internal energy of the initial. The internal energy of a system can be increased by increasing the amount of substance or by giving heat to or by doing work on it. That's why, as I told you, internal energy is extensive property. It is an extensive property. I hope it is clear. So this is called internal energy. It is an extensive property. Next, it is a state function and extensive property. As I already discussed with you, it is a state function and also an extensive property because it is depending on the quantity of matter. The internal energy of an ideal gas. This sentence is very, very important. The internal energy of an ideal gas is a function of temperature only. It is depending on the temperature mainly. Hence, for an isothermal process, already we know isothermal process, delta T is equal to zero. That is change in temperature is equal to zero because temperature is constant involving an ideal gas. So automatically, as delta T is equal to zero, the internal energy, change in internal energy also becomes zero. So the change in internal energy is equal to zero for an isothermal process. This we have seen already in lecture 1. So why it is zero? The change in internal energy is equal to zero for isothermal process because the internal energy of an ideal gas is a function of temperature only, and it does not include pressure, volume, energy. It does not include pressure, volume, energy. I hope it is clear. Next. So this statement is very important. First law of thermodynamics, very, very easy, and it's difficult. It's very easy, and numericals also you'll get from this. So what is first law of kinetic energy? Sorry, first law of thermodynamics. It is same as law of conservation of energy. That is, the total energy of the universe is always conserved. Means either the total energy is always conserved, it is nothing but constant, because if a system loses energy, automatically the other system will gain that energy. So energy is neither created nor destroyed, but can be converted from one form to another form. So which is nothing but law of conservation of energy, and it is same as first law of thermodynamics. The total energy of an isolated system is neither heat is given out now matter is going out. So neither matter or heat is given out to the surroundings. It is called an isolated system. And for an isolated system, the total energy of an isolated system is always constant. This is called first law of thermodynamics. It is similar to law of conservation of energy. I hope it is clear. Next. Mathematical form of first law of thermodynamics. This is important. This they'll ask because based on these formulas, we are going to do numericals from this. So that's why the mathematical form of first law of thermodynamics is important. Consider a system with internal energy U1. Let Q amount of heat to be given to it. So some amount of heat we are giving to that system, and automatically the system will do work. So let W amount of work to be done on it, so that in its new state, its total internal energy becomes U2. Total internal energy becomes how much? It is U2. Automatically the internal energy will change because internal energy depends on the quantity of matter. As we are giving heat to the system, so the work is done on the system, so that it's new it is so that in the new state its total internal energy becomes U2. Now according to first law of thermodynamics, U2 is equal to the internal energy of system plus Q plus W, because there are three types of energy we are giving. And U2 minus U1 is equal to Q plus W. By this, you can say U2 minus U1 is equal to Q plus W. Since U2 minus U1 is equal to delta U, so delta U is equal to Q plus W. This formula is very, very important. And the sign conventions, according to IUPAC conventions, we have to use. So that is what, when work is done on the system, when work is done on the system, W is taken as positive. When work is done by the system, W is taken as negative. And Q also the same way. And delta U, if heat is absorbed by the system, Q is positive. Heat is given out to the by the system, Q is negative. So delta U is called what? On the whole, delta U is equal to, that is first law of thermodynamics. It is equal to delta U, that is change in internal energy, is equal to Q plus W. This is the formula we have to apply for the numericals. So whereas W and Q will be following, Q and W values will be taken. Q and W values will be taken based on IUPAC conventions. Will be taken. Will be taken based on IUPAC conventions. What is IUPAC conventions? In the first PPT we have discussed. So please remember that. It's very, very important. I hope it is clear. So from the first law of thermodynamics, what is the mathematical form you got? Delta U is equal to Q plus W. This formula is very, very important for the entrance exam. So delta U is equal to Q plus W. Simple formula, but lot of confusion will be there while taking the conventions only. That's why you should be thorough with IUPAC conventions. If you are thorough with IUPAC conventions, then only we can easily solve the numerical. Otherwise, you'll be getting a lot of differences. I hope it is clear. Next. Calculation of work done in an irreversible contraction of an ideal gas. Expansion or contraction. In an irreversible expansion or contraction of an ideal gas. Let us see that now. So consider an ideal gas at pressure P. This is an external pressure, so not that one. So consider an ideal gas at pressure P confined in a cylinder of uniform cross section with the help of weightless frictionless piston. So you consider there is a gas inside the cylinder. Let the gas undergo expansion in one step so that the piston moves from the distance. Actually, the gas level is here. So if work is done on the system, automatically the gas will expand. So that expansion will be done. That is called expansion. Let the gas undergo expansion in one step so that the piston moves a distance of L centimeters or meters. That is called length. And the pressure of the gas becomes equal to external pressure, that is P external. So when a system is gaining energy, automatically what happens? The gas expands. When the gas expands, let us note the expansion. So again, you close that. So this is called L is called what? The distance moved by the piston. Now, how to calculate work done? Work done in this case is equal to force into displacement. Since already you know work done is called force into displacement, and the displacement in this case is L, and force is equal to F. And this force is nothing but, so since pressure is equal to, what is pressure? Pressure is equal to force acting per unit area. Since P is equal to F by A, implies F is equal to P into A. That is, A is called area of cross section, and P is called P external, and small a or capital A you can use. So A into L. So from this formula, since pressure is nothing but the force acting per unit area is called pressure. So since P is equal to F by A, we can take F is equal to P into A. So let us take, I'll write in confusion. So capital A one I'll write, where A is called the area of cross section, F is called force. Since pressure is equal to force by area, so force is equal to pressure into area. So by this we can say that is external pressure into area into L. So this L is called, very, very important, this L is called delta V. Why? Because the volume of the system will rise. The distance moved by the system is nothing but piston. A into L is called delta V. A into L is called what? Delta V. So delta V is equal to, that is change in volume is equal to area into distance traveled by the piston. So to confirm the sign convention of work, we can write W is equal to, since work is done by the system, we can say minus P external into delta V, where delta V is called final volume minus initial volume, V2 minus V1. So this formula is also very important in numericals, and very, very important you have to do here. I'll write here. Since pressure is given in atmospheres, pressure is given some atmospheres, and volume will be given in liters. So we will get liter atmosphere, work done in liter atmosphere. So work done you will get from this in liter atmosphere, but the answer they will give in joules. So 1 liter atmosphere is equal to 101.3 joules. So whatever the answer you got, you have to multiply with 101.3, so that you'll get the work done in joules. I hope it is clear. So this convention is very, very important. And to confirm the sign convention of work, we can write W is equal to minus P external delta V minus pressure external pressure into delta V, where delta V is called V2 minus V1, that is final volume minus initial volume. And when you get work done, the work done value in this case, they will give the value of pressure in atmospheres, and they will give the value of volume in liters. And first you have to convert, you have to do V2 minus V1, then P external. So you will get work done in liter atmosphere. When work done is given in liter atmosphere, we will get the value in liter atmosphere. You have to convert them into joules. And what is the conversion? 1 liter atmosphere is equal to 101.3 joules. 1 liter atmosphere is equal to 101.3 joules. So this is very, very important. I hope it is clear. So this is the formula for finding work done of a system. So work done is equal to minus P external into delta V. Remember this formula, very, very important. I hope it is clear. Next, examples. Now you see here, in a process, 701 joules of heat is observed by system. 701 joules of heat is observed by system. Is nothing but what? 701 joules of heat is observed by system. So it is nothing but what it is, nothing but Q. So Q is equal to 701 with a positive sign because it is given to the system plus, and 394 joules of work is done by the system. Here you see the word die by the system. So W is equal to minus 394 joules, because by observing this much of energy, it do some work, and that work is given out as minus 394 joules. Here both in joules only they are given, so no need to change. What is the change in internal energy of the system? Delta U is equal to how much? It's very, very simple. So by this you can say delta U is equal to, in first law of thermodynamics, we got the formula, mathematical formation of first law, mathematical expression of first law of thermodynamics. Delta U is equal to Q plus W. This is the actual formula. Since Q is positive because heat is absorbed by system, so heat is given to the system, observed by system, it is 701 plus minus 394. Very, very important here, because in the examination, the same question they'll give with the different options. I'll tell you the options also. So 701 plus into minus 394 It is equal to 701 minus 394. You can calculate easily, you'll get the answer. Let us see the answer now. So it is equal to 307 joules. It's equal to how much? Plus the 307 joules. So it is equal to plus 307 joules. So this is called internal energy of system. I hope that is change in internal energy of system. I hope it is clear. So in this way you have to do. Let us see the answer now. 307. So in the examination, I'll tell you, they'll give the option like this. What are the options in the examinations also I'll tell you. Option A, 307 joules. Option B, minus 307 joules. Option C, by adding these two, 794 plus 394 plus 701. Just I'll tell you that calculation also. 701 plus 394 is equal to 1095. That is plus 1095 joules. And option D, plus 1095 joules. So you will get like this, either the additive product or the subtractive product. So here we have to do subtraction because work done is taken as negative because work is done by the system. So that's why I told you the IUPAC conventions of the system is very, very important. The IUPAC conventions of the system based on work done and Q is very, very important. Suppose if 701 joules of heat is removed from the system, then Q should be taken as negative. Absorbed and removed, they will give the sentence. So here sentence formation is most important. So try to understand the numerical. The formula is simple, that is delta U is equal to Q plus W. This formula will never change, but there are a lot of confusions. I hope it is clear. So for this sum, as I told you, the options they'll give plus 307, minus 307, minus 1095, plus 1095 joules. So that is addition product, subtraction product with sign conventions, with sign differences. So here answer is what? A option. So I hope it is clear. Next question. So like these questions you are expected for competitive exams. Next question. A gas is compressed by constant external pressure of 1 atmosphere. So here it is nothing but what? External pressure. P external is equal to 1 atmosphere. P external is equal to 1 atmosphere. From a volume of 20 decimeter cube, that is 20 liters, to 10 decimeter cube. So that is V1 is equal to 20 and V2 is equal to 10 because it is compressed 20 liters to 10 liters. In the process, it gives out 500 joules of thermal energy. It gives out. So Q is equal to 500 joules to the surroundings. Calculate the value of internal energy of the system. So change in internal energy of the system you have to calculate. So for this case, first we need to find, since change in internal energy is equal to delta is equal to Q plus W. First we need to find W. So W is equal to minus P delta V. So that is equal to minus 1 into delta V is 20 minus 10. That is 10 minus 20. That is minus 10. Minus 10 and into 101.3 because this is in joules. So work done also because 1 liter atmosphere is equal to 1 liter atmosphere is equal to 101.3 joules. So I'm multiplying this. So W will get the answer. So minus into minus. So you'll get W is equal to negative on the whole. So after multiplying this, you got W is equal to plus 1013 because P is 1, 10 into 1 not 1013. So it is W is equal to plus 1013 joules. And very important, Q is given out. Q is out 500 joules. So Q is taken as negative. So delta U is equal to minus 500 plus 1013. So that's why these sentences are very, very important. Minus 500 plus 1013. You'll get it as 513 joules. 513 joules with positive sign. So this is called the change in internal energy of system. Calculate the value of internal energy change of the system. So delta U you have to find. What is this? Delta U you have to find. Delta U. I hope it is clear. So let us again I revise the problem. So this is taken as V1 and this is taken as V2 because volume from 20 decimeter cube, that is 20 liters, to volume of 10 liters, that's 10 decimeter cube. In the process, it gives out 500 joules of energy. So Q is equal to minus 500. Here I'm writing clearly, just please note it down. Q is equal to minus 500. So Q is equal to minus 500 you have to take, because Q is equal to, again here also I'm writing if you are confusing. So Q is equal to minus 500. So we have V1, we have V2, we have external pressure P. So P external also we got, that is 1 atmosphere. And they are asking us to find delta U, that is delta U. So delta U is called Q plus W. First we need W. So to find W, we have to use the formula. W is equal to minus P delta V, and the value you'll get in liter atmosphere. You have to convert them into joules, because 1 liter atmosphere is equal to 101.3 joules. So minus 1 into minus 10, because 20 minus 10 minus 20, because we have to do V2 minus V1. So 10 minus 20, it becomes minus 10. So minus 10 into 101.3. So you'll get 1013 joules in positive sign. So W is equal to positive, Q is equal to negative, because heat is given out by the system. So delta U is equal to Q plus W, that is minus 500 plus 1013 joules. It is equal to 513 joules. I hope it is clear. Very, very important and easy also. So this conversion is very, very important. So let us check the answer. So it is 513 joules. 513 joules. So please copy down this. I hope it is clear. Let us move to next. Next question. A gas cylinder 5 liter capacity. So it is 5 liter capacity containing 4 kg of helium gas. Here they are given mass. So this is nothing but what? 4 kg of helium gas is nothing but weight of helium gas. W is equal to 4000 grams. At 27 degrees C, temperature is equal to 300 kelvins. Always you have to change the temperature into kelvins. Develop leakage to the leading developed leakage. So some gas is kept in a 5 liter cylinder containing 4 kg of helium. So that is helium gas is kept in a 5 liter capacity at 27 degrees C. Developed leakage to the leading to the escape of the gas into the atmosphere. So due to this leakage in the cylinder, it escapes into the atmosphere. If the atmospheric pressure is 1 atmosphere, calculate the work done by the gas assuming ideal behavior. You need to find calculate work done. Work done is equal to minus P delta V. But here it is different case. So minus P delta V. So work done is equal to what? Minus P delta V. And here what is delta V? First we have to calculate. First volume is given. V1 is given 5 liter capacity, but V2 we have to find. V2 is equal to how much? This is only critical here. So V2 can be found by using ideal gas equation. That is, since ideal gas equation we know PV, since PV is equal to nRT, because they have given weight, number of moles you have to take. So N is equal to weight of helium by molecular weight of helium. So by this we can say V is equal to nRT by P. The P is 1 atmosphere. So that is N is how much? Here N is equal to 4 kg. That is weight by molecular weight. Molecular weight, since N is equal to weight by molecular weight. So weight is given how much? 4 kg. That is can be converted into 4000 grams, because gram molecular weight and gram equivalent weight. So weight in grams by 4 liters, because 4 is the atomic weight of helium. Weight molecular weight of helium is 4 into R value is how much? R value is delta N. That is R value universal gas constant. Since it is in the liters, so it is taken as 8.314 into temperature is 300 kelvins. So I'm writing it here clearly. Four into 8.314 into 300 divided by 4 into 1. So from this you can find out V2 value. So and W is equal to minus P delta V, minus P delta V. And after getting delta V value, we will multiply with, that is, this in this volume is equal to 24,900 liters. That is 24,900 liters. So 24.9. So W is equal to minus, after substituting this, you got V2 is equal to 24,900 ml or 24.9 liters. 24.9 liters we got. So by this you can say minus 1 into delta V value is 5 liters. minus 24.9. Sorry, V2 is 24.9. So I'm changing it again, please see it. So V2 is equal to 24.9 minus 5 liters, that is 5 into 101.3, that you will get in joules. So it is equal to, you'll get 19.9 into 101.3. So you'll get the value of work done like this. After calculating this, you'll get the answer. I hope it is clear. So in the first case, we have to take work done is calculated by using the formula minus P delta V. But since volume 1 is given, volume 2 is not given. So to find volume 2, we have to use gas equation. That is PV is equal to nRT. Since they have given 4 grams of helium gas, so N is equal to weight by molecular weight. That is 4,000 by 4 and into 8.314 into 300 by 4 into 1. This is 1 because they have given 1 atmosphere pressure. So I hope it is clear. Now let us check the answer now. The answer is minus 2494 kilojoules. You have to multiply with this. So you'll get 2494 kilojoules. 2494 kilojoules because it is getting in answering kilojoules. I hope it is clear. Next. Let us see the next question. So next topic in this chapter we'll discuss now. After that, we'll discuss some more questions based on this. So next topic in this chapter, now we are going to do next topic. Work done in an reversible isothermal expansion, very, very important. Work done in an isothermal reversible expansion of an ideal gas. So how to calculate work done in a isothermal. Already you know what is an isothermal process, the process which is taking place at constant temperature. Delta T is equal to 0, also delta U is equal to 0. For isothermal process, what is 0? Delta T is equal to 0. Also, delta U is equal to 0. So from this, we have to calculate work done. So how to calculate this? Now let us see now. A reversible expansion or contraction takes place in a finite number of steps. In an infinite number of steps. So at each stage, P external is equal to P internal plus differentiation of P, that is pressure, during compression, and in equal to P internal minus differentiation of P, that is during expansion. So during compression, we have to add it, and during expansion, we have to subtract it. In general, P external is equal to, already we know, P internal plus or minus change in pressure, that is differentiation of P, that is final pressure. So initial plus final. So dP is nothing but what? Here it is called final. During an isothermal reversible expansion, P external keeps on decreasing infinitesimally slowly because reversible expansion means pressure will decrease, volume will increase. As the pressure decreases, automatically the volume increases. So while the volume of the gas keeps increasing because it is expansion means what is there? Pressure is decreasing and volume is increasing. These two things you have to remember. So while the volume of the gas keeps increasing infinitesimally slowly, so that the system and the surroundings are always at equilibrium. So this is called reversible isothermal expansion. During an isothermal reversible expansion, P external keeps on decreasing and volume keeps on increasing slowly. I hope it is clear. Now how to calculate work done from this, let us see now. So hence for a reversible process, work done during reversible isothermal expansion, negative of, that is because work is done by the system, you have to take it as negative. So integration V1 V2 P external dV, this is the integrated equation. V1 V2, V1 is initial volume, V2 is final volume, P external differentiation of volume. So it is equal to, also equal to differentiation, that is integration P initial plus or minus P final into dV, that is either P1 and P2. So it should be derived up to here. So from this we got this formula. Because this derivation is not required for competitive, so it is discussed in board. So that's why I'm not discussing this. So Work done in reversible isothermal process is equal to, finally, we got the equation that is minus 2.303 nRT. Very, very important formula. Work done in an isothermal reversible expansion is equal to minus 2.303 nRT log of V2 by V1. And T is constant here because reversible expansion, no, T is constant, isothermal process. Also, if suppose if you notice by the means of pressure, we can take log of P1 by P2 because pressure is proportional to 1 by V. So we can say P1 by P2, not P2 by P1. I hope it is clear. So suppose if they are given the values of volumes, you can use this formula. If they are given the values of pressure, of first pressure and second pressure in the isothermal reversible expansion, we can use this formula. So depending on the data in the numerical, we can use any of these two formulas. So this is the formula for finding work done in an isothermal reversible expansion of an ideal gas. The same equation can be used for isothermal reversible contraction also. So either expansion or contraction, we'll use the same equation. I hope it is clear. This formula is very, very important. So how we got this formula? So during an isothermal reversible expansion or contraction, the pressure keeps on decreasing slowly and the volume keeps on increasing slowly. So due to which what happens? The work done can be calculated by using the integration V1, V2, P external dV. dV is called differentiation of volume. And also it can be also be written as minus integration P initial plus or minus differentiation of P differentiation of volume. So you can use this formula, you can use this formula, both are same, and it should be derived up to here. That is work done in a reversible isothermal expansion is equal to, this is the actual formula, application formula for solving numericals, that is minus 2.303 minus 2.303 nRT, where N is called number of moles, R is called universal gas constant, T is called temperature. R value you should take it as 0.0821 or 0.083. And N value, number of moles. N is equal to number of moles. How to calculate number of moles? To find number of moles, weight by molecular weight. Weight by molecular weight. And T is nothing but temperature. You should take temperature in kelvins only because capital T means absolute temperature. So temperature in kelvins. And V2 is called final volume. V1 is called initial volume. Similarly, P1 is called final initial pressure, P2 is called final pressure. Why we got P1 by P2, whereas here V2 by V1, since from Boyle's law we know P is inversely proportional to V. So P is proportional to 1 by V. So that's why you got P1, 1 by P2 by P1, it becomes P1 by P2. So the same equation can also be used for isothermal reversible contraction. So please note down these formulas. Wherever it is necessary, we have to do it. I hope it is clear. Next, graphical representation of work done. Graphical representation of work done and work in an isothermal reversible process, reversible expansion. Let us see now. So shaded area under the curves is a measure of the amount of work done. So work done is equal to shaded part. This part is called work done because volume here, external pressure is applied. So volume changes from V1 to V2. Here by applying pressure is kept constant. So volume changes from V1 to V and V to V2 finally. So this is irreversible expansion in multiple steps. And this is isothermal reversible expansion. Isothermal reversible expansion, the graph will be the pressure decreases from P1 to P2 and volume increases from V1 to V2. I hope these are the graphs. These graphs are also important because they'll ask base graphical question. So what is work done in this case? Shaded part is called work done. So shaded part means here like this shaded part and this is shaded part and here also shaded part. So you'll get area of rectangles, 1, 2, 3, 4 rectangles like that. Here also rectangle. So this is shaded part is called work done. So work done is equal to shaded part. I hope these are clear. So these graphs are also important. So it is the graph for work done in irreversible expansion in one step, irreversible expansion in multiple steps, isothermal reversible expansion in one step or multiple steps. So this is the concept. I hope it is clear. So these graphs are important. Please note down in your classworks. So how to calculate work done? The shaded part of the system is of the graph is nothing but the work done of the system. And based on the shaded part, if it is a rectangle, we'll take it as length into breadth. If it is triangle will take half into base into height, like that, depending on the system. I hope it is clear. Next, very, very important. The work done during free expansion, because work is done by itself. So that's why expansion of gas into vacuum, or the work done expansion of gas into vacuum is called free expansion. And for free expansion, since P external is equal to 0, because the gas is changing into vacuum, expansion of gas into vacuum taking place. So P external is equal to 0. So it is called as free expansion. And during free expansion, since P is equal to 0, automatically work done is also equal to 0. So work done in free expansion is always 0. Please note down the sentence. Work done of a gas by itself, or free expansion, free expansion is always equal to 0, because in this case P external is equal to, since P external is equal to 0, so that's why work done in free expansion is always equal to 0. Work done of a gas in free expansion, wherever you see the word free expansion, we can say it is equal to 0. Or whenever you see the word expansion of gas into vacuum, it is called as free expansion. What is free expansion? Expansion of a gas into vacuum. Expansion of a gas into vacuum is called free expansion. I hope it is clear. So this is called work done. Next. So this statement is very, very important. Please note down in your classworks. Now let us see the questions based on this. 2 liter of an ideal gas. 2 liter. So volume V1 is 2 liters. V1 is equal to 2 at 10 atmospheric pressure. So expands until its volume becomes 10 liters. So V2 becomes 10 liters and P is equal to 10. How much heat is absorbed, how much work is done, when. So heat also we need to find. What is heat? Delta H. Delta H or H. So delta H or H, that is heat. So how much heat is absorbed and how much work is done when gas expands isothermally into vacuum. Isothermally into vacuum. So when the gas is expand isothermally into vacuum, work done is always equal to 0. Similarly, when the gas expands isothermally against a constant pressure of 1 atmosphere, here external pressure P external is equal to 1 atmosphere. So that's why, since it is equal to 1 atmosphere, so it is not changing into EC. So free expansion of the gas. So we can use the formula work done is equal to minus P delta V. Work done is equal to minus P delta V in this case. So work done is equal to minus P delta V means minus 1 into delta V. Volume is changing from 10 to 2 liters to 10 liters. So it is nothing but V2 minus V1, that is 10 minus 2. So it is equal to minus 1 into 8 into 101.3 joules, because this is given in liter atmosphere, work done will be given in joules. So that is equal to how much? It is equal to 8 into 101.3 into minus 1. So it is equal to 801.4, I believe, or 804.1. So 801.4 joules. So this is the second case work done. First case work done is equal to 0, and second case work done is equal to this. In the same way, how much gas expands in a reversible manner. So in reversible manner, delta H and W is equal to, in reversible manner, W is equal to, we can find in third case, W is equal to minus 2.303 nRT log of V2 by V1, or P1 by P2. So V2 by V1. So substitute this formula, you'll get second case, third case also, you'll get work done in joules. I hope it is clear. Let us check the answer now. So first case it is 0, as I told you. Second case it is minus 810. This is minus because here I have to write, I forgot to write minus here because this is minus anyway. So minus 801, 810. So it is 810, 810.4 joules. And third case it is minus 3.26 kilojoules. Kilojoules means it should be minus 3.26, sorry, into 1000 joules. So third case you have to see, check this using this formula in third case, because n is taken as, here n is not given, so you take it as n is equal to 1 mole, And T, temperature, you take it as room temperature, that is 298 kelvins. 298 kelvins. So 298 kelvins. So automatically you'll get the answer. I hope it is clear. And V2, V1 we already know. So you'll get 3.26 into 1000 joules. And take in this case R is equal to 8.314. Once again, I repeat the question. So how much heat is absorbed and how much work is done when gas expands isothermally into vacuum? When the gas expands isothermally into vacuum, it is called free expansion. Since it is free expansion, we can say W is equal to 0, work done is equal to 0 in this case. Second case, gas expands isothermally against a constant pressure of 1 atmosphere. So this is pressure against external pressure. So P external is equal to 1 atmosphere and W is equal to minus P delta V. So minus P delta V is equal to minus 1 into volume is given 10 liters to 2 liters. So 10 minus 2, it is 8. And since it is liter atmosphere and the answer will be given in joules, so we have to multiply with 101.3 joules. So minus 1 into 8 into 101.3, we got it as 810.4 joules. I hope it is clear. And in third case, how to calculate work done? Work done is equal to minus 2.303 nRT log of V2 by V1. And what is heat is observed Q? Since Q is equal to, already you know how to calculate Q, I'll tell you live right now. Please listen now, because we have not discussed only work done, we have discussed. In first case, W is equal to 0 means Q is also equal to 0, because isothermal process means delta U is equal to 0. So in isothermal process, delta U is equal to 0 means automatically Q becomes minus W. Q becomes what? Minus W, because from first law of thermodynamics we know delta U is equal to Q plus W. So Q becomes minus W. So whatever the value you got, you take it to the value in. So in this case, Q is equal to plus, in this case, Q is equal to plus 810.4 joules. And in this case, Q is equal to plus 3.26 kilojoules. So because Q is equal to minus W, because this is isothermal process. Since it is isothermal process, we can say for all isothermal process, delta U is equal to 0. Since delta U is equal to 0, from the first law of thermodynamics, we know delta U is equal to Q plus W. What is Q? Q is heat is absorbed. Q is heat. So Q is equal to minus W. So in the first case, W is equal to 0, so automatically Q becomes 0. In second case, W is equal to minus 810.4 joules. So Q becomes plus 810.4 joules. In third case, W is equal to minus 3.26 joules, kilojoules. So automatically Q becomes plus 3.26 kilojoules. I hope it is clear. So very, very important this model. You will get this type of questions in competitive exams, entrance exams. I hope it is clear. Next. Next, enthalpy or heat of heat. So enthalpy is a state function. Enthalpy is a state function. Already we know it is a state function like internal energy, useful while dealing with the processes at constant temperature. From first law, we know delta U is equal to Q plus W, or Q is minus P delta V, because work done is equal to minus P delta V. At constant pressure, QP is equal to, at constant pressure, QP is equal to, that is heat is equal to, delta U plus P delta V, that is U2 minus U1 plus P into V2 minus V1, or U2 minus E1 plus PV into PV2 minus PV1, or QP is equal to U2 plus PV2 minus U1 plus PV1. Since U, that is internal energy, P, pressure and volume are state functions, U plus PV is also a state function, and it is called enthalpy. By this you can see enthalpy is equal to H is equal to U plus PV, where H is called enthalpy. So we got the new formula, enthalpy is equal to U plus PV. What is U? Internal energy plus P is called pressure and volume. So pressure into volume is called work and U is called internal energy. So heat is equal to U plus PV. Is a new formula we got based on enthalpy. So how to calculate enthalpy or heat of system? We have to use this formula. I hope it is clear. Continuation. Enthalpy or heat content. Continuation. QP is equal to H2 minus H1. That is QP is equal to delta H. So delta H is called heat absorbed at constant pressure by process at constant pressure. Therefore, delta H is equal to, very, very important, delta H is equal to delta U plus P delta V. That is change in enthalpy for a process at constant pressure. The change in enthalpy for a process at constant pressure is given as the formula delta H is equal to delta U plus P delta V. where delta H is if delta H is positive, we can say heat is absorbed, that is endothermic process. And if delta H is negative, we'll say heat is given out, that is exothermic process. So it is almost equal to Q. Almost equal to Q. So this is very, very important formula. Now let us see the questions based on this also. Again, apart from this, now relation between delta H and delta U. This is most important. For every time from JE mains, they'll ask from this formula only. So how to calculate relationship between delta H and delta U in chemical thermodynamics, chemical reactions. So let N1 and N2 number of moles. So number of moles of gases, reactants, and products respectively. And V1 and V2 is called total volume of gases, gaseous reactants. Very important, gaseous reactants and products. Suppose if the reactants or products are not in gaseous state, N1 and N2 is becomes zero, and we will not consider that. Total volume of gaseous reactants and products now respectively. So delta H is equal to delta U plus P delta V. So delta U is equal to P in delta U plus P into V2 minus V1, or delta U plus PV2 minus PV1. This is the formula. Now, next question, next condition. So these formulas are very easy to understand. Please note it down. And now at constant temperature and pressure, let us take the condition constant temperature and pressure. So P1, PV1 is equal to N1 RT and PV2 is equal to N2 RT, because pressure is constant, volume is changing. So N1, N2. So by this we can say N1 plus N2 is equal to, so delta H is equal to delta U plus N2 RT minus N1 RT, or delta U plus RT, that is N2 minus N1. Taking N2 minus N1 common, we can take N2 minus N1 into RT. By this we can say, since N2 minus N1 RT, since N2 minus N1 is equal to delta N, that is delta Ng, number of moles of gases. So number of moles is equal to delta N is equal to number of moles of gaseous products, number of moles of, this is very important, number of moles of gaseous products minus number of moles of gaseous reactants. Gaseous reactants. So delta N. For example, now we take N2 plus 3H2 gives us to 2NH3. All are gases. So how to calculate delta N for this? Suppose N2 is gas, H2 is gas, and this is also gas. So how to calculate delta N? Delta N is equal to products. Number of moles of products is 2, because ammonia, 2 moles of ammonia, 2 minus, and 3 plus 1, because this is 1 mole. So 3 plus 1, 2 minus 3 plus 1, that is 4, that is equal to minus 2. So like this, you have to calculate delta N like this. So delta N is called what? Delta N is equal to number of moles of gaseous products minus number of moles of gaseous reactants, delta Ng. So by this you can say delta H is equal to delta U plus delta N RT. This equation is very, very important. From this, definitely you will get question for all entrance exams. So how to calculate heat of change, change in enthalpy of the system. Change in enthalpy of system is equal to change in internal energy plus delta N RT, where R is called gas constant, T is called temperature. Temperature in absolute temperature. So I hope it is clear. Very, very important formula. Let us see the application of this formula now. For a gaseous reaction, now we are applying thermodynamics in chemical reactions. So for a gaseous reaction, 2 moles of A2 plus 5 moles of B2, both are in gaseous state, combines to form 2 moles of A2B5. Let us consider at 27 degrees C. The heat change at constant pressure is found to be minus 50160. That is called heat change at constant pressure is what? Minus 50160 joules. That is 50,160 joules. Calculate the value of internal energy change delta U, given that R is equal to 8.314. So they have given R value. Now we need to consider this formula by using the formula delta H is equal to change in enthalpy is equal to delta U minus delta U plus delta nRT. And they have given delta H value is already given. This is called delta H, the heat change, that is enthalpy change at constant pressure is given. This is delta H. And these are nothing but, so delta N value, how to calculate delta N is equal to number of moles of products minus number of moles of reactants. That is, products is 2 minus 5 plus 1, 6. Because 2 moles of A2B5, 5 plus 1, 2 minus 5 plus 1, that is 6. 2 minus 6 is equal to minus 4. So delta N is equal to minus 4. And R value we know, temperature is given as 300 kelvins. Temperature is equal to 300 kelvins because 273 plus 27. Now using this formula, delta H is equal to delta U plus, by this you can say delta U is equal to how much? Delta U is equal to delta H minus delta N RT. Now substituting this formula directly, so delta H is given minus 50,160 joules minus, what is the value of delta N? Delta N is minus 4 into R value 8.314, it is already given, into temperature is 300. So by calculating this, we got minus 50,160 minus of minus 4 into 8.300, that is 1200 into 8.314. We got it as totally minus 12,471. So minus of minus becomes plus. So minus 50,160 plus 12,471 joules is equal to, it is equal to minus 37689 minus 37,689 joules. So this is the answer. So that is called delta U is equal to, that is change in internal energy of the system. Change in internal energy of the system is equal to minus 37689 joules. I hope it is clear. It's very, very important. So delta H is equal to delta H minus delta U is equal to delta H minus delta nRT. So let us check the answer now. So it is minus 37689 joules. So what is the question here? A gaseous reaction is given in which 2 moles of A2 plus 5 moles of B2 gives rise to 2 moles of A2B5. This is product and these are reactants. And the heat change at constant pressure is found to be minus 50,160 joules. That is delta H value is given. And the heat change means delta H. That is enthalpy change. Calculate the value of internal energy change, delta U they are asking. Now we already know delta H is equal to delta U plus delta nRT. This is the first law of thermodynamics chemical reaction formula. So delta H is equal to delta U plus delta nRT, and we need to find delta U. Delta U is equal to delta H minus delta nRT. So what is delta N value? Number of moles of products minus number of moles of reactants. That is 2 minus 5 plus 1, 5 plus 2. Sorry, it is 5 plus 2. And let us change it. 5 plus 2, that is 7. 2 minus 7, it is equal to minus 5. So here also I'm writing minus 5. Anyway, value will get the same. So if I got to bring minus 5, so 5 into 8.314 into 300. So temperature is equal to 300 kelvins. So automatically you'll get the value of delta U value. I hope it is clear. Very, very important model. This model is very important. So please note down in your classworks. I hope you have noted it. Now I'm playing the track. Next. Delta H, delta E, Q, and W in isothermal expansion contraction process. What is the value of delta H, delta U, Q, and W? What is delta H? Enthalpy change. What is delta U? Change in internal energy. What is Q? Q is called heat observed or heat given out. What is W? Work done in isothermal expansion or contraction process. Let us discuss now. So for an ideal gas, H and U are functions of temperature only. That is and enthalpy and internal energy are functions of temperature only. Hence at constant temperature, since isothermal process means constant temperature. So at constant temperature, delta H is equal to delta U is equal to 0. So for isothermal process, we can say delta H, delta U is always 0, and also delta T is also equal to 0. So what are the three for isothermal reversible expansion or isothermal process, expansion or contraction? Delta H is equal to 0. This they will ask in the objective. Which of the for isothermal expansion of gases, which is correct? For that, change in enthalpy is equal to 0. Change in internal energy for that system is also equal to 0, and change in temperature is also equal to 0. Very, very important for an ideal gas. This they'll ask in entrance exam. According to the first law of thermodynamics, delta U is equal to Q plus W, or Q 0 is equal to Q plus W, implies Q is equal to minus W. This numerical already we have done in the previous sessions. For an isothermal reversible expansion, for an isothermal irreversible change, Q is equal to minus W, that is Pxn into V2 minus V1. Or for an isothermal reversible change, Q is equal to minus W, that is 2.303 nRT log of V2 by V1. So irreversible change, P external V2 minus V1 and reversible change 2.303 nRT log of V2 by V1 because minus of minus becomes plus. So here you got this. So for isothermal reversible expansion, Q is equal to 2.303 nRT into log of V2 by V1 because Q is equal to minus W. Minus minus becomes positive. I hope it is clear. Very, very important. Next continuation. Example 3. Calculate W, Q, delta U and delta H when 2 moles. So N is equal to 2 of an ideal gas contracts isothermally and reversibly from a volume of 25 liters to 15 liters. So V1 is equal to 25 and V2 is equal to 15 and temperature T is equal to 300 kelvins. So simple, directly use the formula. So Q is equal to minus W. So if you know W, automatically you will get all the things. And since delta U and delta H becomes 0 because this is isothermal process, so delta U is equal to 0, delta H is equal to 0. Isothermally because delta U is equal to 0 and delta H is equal to 0. So only we need to find W. So how to calculate W? W is equal to minus 2.303 nRT log of V2 by V1. Direct substitution. So that is equal to minus 2.303. N value is 2 moles. R value is 8.314. Temperature value is 300 kelvins. It is already given into log of V2 by V1. V2 is 15 and V1 is 25. So 15 by 25. This becomes 3, 5, 5 3 is a 5 5 is a. So log of 3 by 5 can be taken as, this can be taken as minus 2.303 into 2 into 8.314 into 300 into log A by B is taken as log 3 minus log A minus log B, log 3 minus log 5. So log 3 value is 0.4771. So log 3 is equal to 0.477 and log 5 value is equal to 0.698 approximately. So this can be taken as, I will write it here. It is not clear, not visible. So log 3 value is equal to 0.477. 477 log 3 value. So you can take this and substitute these values, you'll get the answer. I hope it is clear. Let us check the answer now. 100% you get the answer. The answer is equal to minus 2549 joules. Minus, so that is work done. Let us check the answer. So 2514 joules, that is work done only. Work done here minus, so here also minus, so minus minus becomes plus. So Q is equal to minus 2549, whereas work done is equal to positive, that is plus 2549. So here work done is equal to, I am writing here work done. After substituting this value, work done is equal to plus 2549 joules. And Q is equal to minus 2549 joules. This is the value of Q because Q is equal to minus W. I hope it is clear. So this type of questions are most important, easy to understand and easy for substitution. Only calculation part is bigger. So we need to thorough with the multiplications. Approximate values you can take. I hope it is clear. Next. So with this, I'm ending the session. So in this session, we have done very, very important numericals. It's very, very important. I hope it is clear. Practice this type of questions in the examination by using complete entrance exam books. I hope it is clear. Thank you.